Hi everyone. In today's lecture we will do a review of Module 2. This will be an overall review of all the topics and important concepts that you have seen in Module 2. Hopefully this will help you to develop a summarized content in your mind and be able to apply it to different problems that you have in your homeworks or the problem that you will see in the final quiz. If you remember, we started Module 2 with the idea of momentum equation. From the last section covered in Module 1 and also the very early lectures of Module 2, you will remember that if we have a fluid element, we can actually write down the balance of momentum for this fluid element, bring it to the limit of infinitesimally small volumes, such as the one that I've drawn in an exaggerated manner on the board here, and then reach to the conclusion that there are three major terms or forces or sometimes fictitious forces in this case, involved in the whole dynamics. There are certain surface forces that are captured through what we call the gradient of the stress tensor. Those are shown by the magenta color, and that's the grad operator acting on the tau, which is the stress tensor. There is definitely body force, which is the weight of the fluid element per unit volume, rho g. If the gravity is pointing downward, that rho g is also parallel to the vector of gravity. And the sum of these two will set the net inertia or the acceleration of fluid element. Mass times acceleration per unit volume would be density times acceleration. And if you like, sometimes people show negative rho a as a vector that will act almost like a fictitious force. So the summation of these three vectors should be equal to 0. Or in other words, you can say that the summation of these two should give you rho a, which will be in this direction. That's the main idea. That's the main balance of forces acting on a fluid element. The summation of forces due to surface summation of surface forces, which is captured by the gradient of the stress tensor, and body forces should balance with the fluid acceleration per unit volume. That's what we wrote down as the Cauchy momentum equation. Left-hand side is the inertia, right-hand side has the surface forces and body forces as written here. The very important term that we spent quite a bit of Module 2 explaining how to calculate it and how to manipulate it is the idea of the stress tensor. And a stress tensor, if you like to think about it, is nothing other than the summation of a unit tensor which has a prefactor known as pressure minus P multiplied to I, plus viscous contributions, which come as viscosity multiplied to grad V, gradient of the velocity tensor, plus its transpose, grad V transpose, which is the symmetric part of the gradient of the velocity tensor. This representation is valid only for incompressible Newtonian liquids and we showed that once we use this relationship between deformation rates, which are captured through this term here, and the overall stress tensor through a constant that we defined as the viscosity mu, we say that this linear relationship that we use for Newtonian liquids is an example of a constitutive equation. For Newtonian liquids such as water, air, simple oils, and many other materials that we have around ourselves, simple liquids, this is definitely a very good constitutive equation and good approximation to use for a constitutive equation. However, there are some non-Newtonian fluids and more complex type of fluids that have slightly more complex and sometimes non-linear type of constitutive equations for themselves. We are not really dealing with them in 225. So as far as you are concerned, in 225, this equation is almost valid for every liquid that you choose. Now that we have this relationship, we could actually plug this inside the Cauchy equation and see what would be the consequence of that. If I do that, I would get an interesting relationship. So again, the left-hand side will be the same. That would be acceleration per unit volume, rho dv over dt, is equal to, so inertia per unit volume on the left-hand side. On the right-hand side, when I put these and take the grad operator acting on these two, the pressure will be just negative grad P that comes out. And then we showed that if you actually take this part, the viscous contribution to the overall stress tensor, and apply the grad operator on that, you will get the Laplacian of the velocity vector. So you will get something that looks mu del squared multiplied to the velocity vector v. And finally, we will have the final term as it was written in the Cauchy equation, which is the body force is the weight of fluid element per unit volume, and that's rho g. We mentioned that this new equation is slightly different from the Cauchy equation. We assumed a constitutive equation that belongs to incompressible Newtonian liquids, and doing that, we derived a new equation that we called it Navier-Stokes equation. So again, to remind ourselves, this is a vectorial form of conservation of linear momentum. It's written in a vectorial form, which means that this equation indeed has three components. In a Cartesian coordinate system which has coordinates x, y, z, we will have three components for this equation. And for some problems, or for many problems indeed, we need to look at all three components. To solve Navier-Stokes equation, we need to keep in mind three important things. So I'm going to list them here. And this will be a new part, which is solving Navier-Stokes equation, which sometimes we use the abbreviation NSE. And the 3 points that we need to keep in mind are the fact that this is a second order equation because we have a second derivative for velocity here. So when we solve this equation, we often have to integrate twice, and we often get constants of integration every time we integrate. To find those constants of integration, what we need are certain types of boundary conditions. One famous boundary condition is the no-flux boundary condition when you get close to a wall. So that's one boundary condition to keep in mind. Another famous boundary condition, as we discussed, is the no-slip boundary condition, which means when you have a wall, not only fluid elements cannot enter it, you cannot have a flux through the wall, but also you have the no-slip condition, which means if you have a fluid element and reach the surface, you are basically having zero tangential velocity. There is no way you can have a velocity that is non-zero if the wall is a station. If the wall is moving, means that your fluid element will move at the wall. Fluid elements move with the wall with exactly similar velocity. These two were relatively straightforward. The third condition that we mentioned and we use in certain problems is what we call continuity of a stress, which is equivalent to saying continuity of momentum flux. This idea was extensively used, especially in free surface boundary conditions. And if you remember, this means that not only velocity should be continuous when you cross from one phase to another phase in the interface between the two phases, but also the shear stress should remain continuous. In other words, if you go from oil to air or oil to water, at the interface, the shear stress in the oil and the shear stress in the water should have exactly same values. And sometimes based on the mismatch between viscosities of oil and water, we found that that means that gradients of velocity are negligible in the more viscous medium or more viscous phase, and they are mostly concentrated in the less viscous phase. That was one condition that we used. Now that we saw all these concepts together, we will look at one example in the next video and see how we can combine this and think about the solution in terms of velocity field for a case where viscous effects are not negligible, but are indeed important and they play a key role. This will be what we will do in the next video.